Managing growing projects with packages, crates, and modules. As you write large programs, organizing your code will be important because keeping track of your entire program in your head will become impossible. By grouping related functionality and separating code with distinctive features, you'll clarify where to find code that implements a particular feature and where to go to change how a feature works. The programs we've written so far have been in one module in one file. As a project grows, you can organize code by splitting into multiple modules and then multiple files. A package can contain multiple binary crates and optionally one library crate. As a package grows, you can extract parts into separate crates that become external dependencies. This chapter covers all the techniques. For very large projects, a set of integral packages that evolve together. Cargo provides workspaces, which we'll cover in the Cargo Workspaces section in Chapter 14. In addition to grouping functionality, encapsulating implementation details lets you reuse code at a higher level. Once you've implemented an operation, other code can call that code via the code's public interface without knowing how the implementation works. The way you write code defines which parts are public for other code to use and which parts are private implementation details that you reserve the right to change. This is another way to limit the amount of detail you have to keep in your head. A related concept is scope. The nested context in which code is written has a set of names that are defined as in scope. When reading, writing, and compiling code, programmers and compilers need to know whether a particular name at a particular spot refers to a variable, function, struct, enum, module, constant, or other item, and what that item means. You can create scope and change the names. You can create scope and change which names are in or out of scope. You can't have two items with the same name in the same scope. Tools are available to resolve name conflicts. Rust has a number of features that allow you to manage a code's organization, including which details are exposed, which details are private, and what names are in each scope in your programs. These features, sometimes collectively referred to as the module system, and include packages, a cargo feature that lets you build, test, and share crates. Crates, a tree of modules that produces a library or executable. Modules and use let you control the organization, scope, and privacy of paths. Paths, a way of naming an item such as a struct, function, or module. In this chapter, we'll cover all these features, discuss how they interact, and explain how to use them to manage scope. By the end, you should have a solid understanding of the module system and be able to work with scopes like a pro. Packages and crates. The first parts of the module system we'll cover are packages and crates. A crate is a binary or a library. The crate root is a source file that the Rust compiler starts from and makes up the root module of your crate. We'll explain modules in more depth in the Defining Modules to Control Scope and Privacy section. A package is one or more crates that provide a set of functionality. A package contains a cargo toml file that describes how to build those crates. Several rules determine what a package can contain. A package must contain 0 or 1 library crates and no more. It can contain as many binary crates as you'd like, but it must contain at least one crate, either library or binary. Let's walk through what happens when we create a package. First, we enter the command cargo new. When we entered the command cargo, created a cargo toml file giving us a package. Looking at the contents of cargo toml, there's no mention of source/main.rs because cargo follows a convention that source/main.rs is the crate root of the binary crate with the same name as the package. Likewise, cargo knows that if the package directory contains source/lib.rs, the package contains a library crate with the same name as the package, and the src/lib.rs is its crate root. Cargo passes the crate root files to rustc to build the library or binary. Here we have a package that only contains src/main.rs, meaning that it only contains a binary crate named my-project. If a project contains src/main.rs and src/lib.rs, it has two crates, a library and a binary, both with the same name as the package. A package can have multiple binary crates by placing files in the src/bin directory. Each file will be a separate binary crate. A crate will group related functionality together in a scope so that the functionality is easy to share between multiple projects. For example, the rand crate we used in Chapter 2 provides functionality that generates random numbers. We can use that functionality in our own projects by bringing the rand crate into our project scope. All the functionality provided by the rand crate is accessible through the crate's name rand. Keeping a crate's functionality in its own scope clarifies whether particular functionality is defined in our crate or the rand crate and prevents potential conflicts. For example, the rand crate provides a trait named RNG. We can also define a struct named RNG in our own crate. Because a crate's functionality is namespaced in its own scope, when we add rand as a dependency, the compiler isn't confused about the name RNG. What the name RNG refers to. In our crate, it refers to the struct RNG that we defined. We would access the RNG trait from the rand crate as rand RNG. Let's move on and talk about the module system. Defining modules to control scope and privacy. In this section, we'll talk about modules and other parts of the module system, namely paths that allow you to name items, the use keyword that brings a path into scope, and the public pub keyword to make items public. We'll also discuss the as keyword external packages, and Glob Operator. For now, let's focus on modules. Modules let us organize code within a crate into groups for readability and easy reuse. Modules also control the privacy of items, which is whether an item can be used by outside code, public, or is an internal implementation detail and not available for outside use, private. As an example, let's write a library crate that provides the functionality of a restaurant. We'll define the signatures of functions but leave their bodies empty to concentrate on the organization of the code rather than the actual implementation of restaurant in code. In the restaurant industry, some parts of the restaurant are referred to as front of house and others back of house. Front of house is where customers are. This is where hosts seat customers, servers take orders and payment. The bartenders make drinks. Back of the house is where the chefs and cooks work in the kitchen. Dishwashers clean up and managers do administrative work. To structure our crate in the same way that a real restaurant works, we can organize the functions into nested modules. Create a new library named restaurant by running cargo new --lib restaurant. Then put the code in listing 7-1 into src/lib.rs to define some modules and function signatures. Listing 7-1, a front _ house module containing other modules that contain functions. We define a module by starting with the mod keyword and then specify the name in the module. In this case, front _ house, and place curly brackets around the body of the module. Inside modules, we can have other modules, as in this case, the module hosting and serving. Modules can also hold definitions for other items, such as structs, enums, constants, traits, or as in listing 7-1, functions. By using modules, we can group related definitions together and name why they are related. Programmers using this code would have an easier time finding the definitions they wanted to use because they could navigate the code based on the groups rather than having to read through all the definitions. Programmers adding new functionality to this code would know where to place the code to keep the program organized. Earlier we mentioned that source/main.rs and source/lib.rs are called crate roots. The reason for their name is the context of either of these two files form a module named crate at the root of the crate's module structure known as the module tree. Listing 7-2 shows the module tree for the structure in listing 7-1. Listing 7-2, the module tree for the code in listing 7-1. This tree shows how some of the modules nest inside one another. For example, hosting nests inside front of house. The tree also shows some modules are siblings to each other, meaning they're defined in the same module, hosting and serving, but are defined within front of house. To continue the family metaphor, if module A is contained inside module B, we say that module A is the child of module B, and that module B is the parent of module A. Notice that the entire module tree is rooted under the implicit module named crate. The module tree might remind you of the file system directory tree on your computer. This is very apt. This is a very apt comparison. Just like directories in a file system, you use modules to organize your code, and just like files in a directory, we need a way to find our modules. Paths for referring to an item in the module tree. To show Rust where to find an item in a module tree, we use paths in the same way we use paths when navigating a file system. If we want to call a function, we need to know its path. A path can take two forms. An absolute path starts from a crate root by using the crate name or a literal crate. A relative path starts from the current module and uses self, super, or an identifier in the current module. Both absolute and relative paths are followed by one or more identifiers separated by double colons. Let's return to the example in 7-1. How do we call the add_to_waitlist function? This is the same as asking what's the path of the add_to_waitlist function. In listing 7-3, we simplified our code a bit by removing some of the modules and function. We'll show two ways to call the add_to_waitlist function from a new function eat_at_restaurant defined in the crate root. The eat_at_restaurant function is part of our library's crate public API. So we mark it with the pub keyword in the exposing paths with the pub keyword section. We'll go into more detail about pub. Note that this example won't compile just yet. We'll explain why in a bit. Listing 7-3, calling the add_to_waitlist function using absolute and relative paths. The first time we call the add_to_waitlist function in eat_at_restaurant, we use an absolute path. The add_to_waitlist function is defined in the same crate as eat_at_restaurant, which means we can use the crate keyword to start an absolute path. After crate, we include each of the successive modules until we make our way to add_to_waitlist. You can imagine a file system with the same structure, and we'd specify the path /front_of_hosting/add_to_waitlist to run the add_to_waitlist program. Using the crate named to start from the crate root is like using / to start from the file system root in your shell. The second time we call add_to_waitlist in each eat_at_restaurant, we used a relative path. The path starts with front_of_house, the name of the module defined at the same level of the module tree as eat_at_restaurant. Here the file system equivalent would be using the path front_of_house/hosting/add_to_waitlist. Starting with a name means that a path is relative. Choosing whether to use a relative or absolute path is a decision you'll make based on your project. The decision should depend on whether you're more likely to move an definition code separately from or together with the code that uses the item. For example, if we move the front_of_house module and the eat_at_restaurant function into a module named customer_experience, we'd need to update the absolute path to add_to_waitlist, but the relative path would still be valid. However, if we moved eat underscore at underscore restaurant function separately into the module named dining, the absolute path to the add underscore to underscore waitlist call would stay the same, but the relative path would need to be updated. Our path our preference is to specify absolute paths because it's more likely to move code definitions and item calls independently of each other. Let's try to compile listing 7-3 and find out why it won't compile yet. The error we get is shown in listing 7-4. Listing 7-4, compiler errors from building the code in listing 7-3. The error message says that the module hosting is private. In other words, we have the correct paths for the hosting modules and the add underscore to underscore waitlist function, but Rust won't let us use them because it doesn't have access to the private sections. Modules aren't useful only for organizing your code. They also define Rust's privacy boundary. The line that encapsulates the implementation details the external code isn't allowed to know about, call, or rely on. So if you want to make an item like a function or a struct private, you put it in a module. The way privacy works in Rust is that all items, function, methods, structs, enums, modules, and constructs are private by default. Items in these parent modules cannot use the private items inside child modules, but items in child modules can use the items in their ancestor modules. The reason is child modules wrap and hide their implementation details, but the child module can see the context in which they're defined. To continue with the restaurant metaphor, think of privacy rules as being like the back office of a restaurant. What goes on in the is private to the restaurant customers, but office managers can see and do everything in the restaurant in which they operate. Rust chose to have the module system function this way so that hiding inner implementation details is the default. That way, you know which parts of the inner code you can change without breaking outer code. But you can expose inner parts of the child module code to outer ancestor modules by using the pub keyword to make an item public. Exposing paths with the pub keyword. Let's return to the error in listing 7-4 that told us the hosting module is private. We want the eat at restaurant function in the parent module to have access to the add underscore to underscore waitlist function in the child module. So we mark the hosting module with the pub keyword as shown in listing 7-5. Listing 7-5, declaring the hosting module as pub to use it from eat underscore at underscore restaurant. Unfortunately, the code listing in 7-5 still results in an error as shown in listing 7-6. Listing 7-6, compiler errors from building the code in listing 7-5. What happened? Adding the public keyword in front of the mod hosting makes the module public. With this change, we can access the front underscore of underscore house. We can access hosting, but the contents of hosting are still private. Making the module public does not make its contents public. The pub keyword on the module only lets code in its ancestor module refer to it. The errors in 7-6 say that the add underscore to underscore waitlist function is private. The privacy rules apply to structs, enums, functions, and methods as well as modules. Let's also make the add underscore to underscore waitlist function public by adding the pub keyword before its definition, as in listing 7-7. Listing 7-7, adding the public keyword to modify hosting and function add underscore to underscore waitlist lets us call the function from eat underscore at underscore restaurant. Now the code will compile. Let's look at the absolute and the relative path and double check why adding the pub keyword lets us use these paths in add underscore to underscore waitlist with respect to the privacy rules. In the absolute path, we started with crate in the root of our crates module tree. Then the front underscore of underscore house module is defined in the crate root. The front underscore of underscore house module isn't public. But because the eat underscore at underscore restaurant function is defined in the same module as front underscore of underscore house, that is, eat underscore at underscore restaurant and front underscore of underscore house are siblings. We can refer to front underscore of underscore house from the eat underscore at underscore restaurant. Next is hosting module marked with pub. We can access the parent module of hosting, so we can access hosting. Finally, the add underscore to underscore waitlist function is marked with pub, and we can access its parent's module, so the function call works. In the relative path, the logic is the same as absolute path except for the first step. Rather than starting from the crate root, the paths start from front underscore of underscore house. The front underscore of underscore house module is defining within the same module as eat underscore at underscore restaurant. So the relative path starting from the module in eat underscore at underscore restaurant is defined works. Then because hosting a add underscore to underscore waitlist are marked with pub, the rest of the path works and this function call is valid. Starting relative paths with super. We can also construct relative paths that begin in a parent module by using super at the start of the path. This is like starting a file system path with the ... syntax. Why would we want to do this? Consider the code listing 7-8 that models the situation in a chef fixes an incorrect order and personally brings it out to the customer. The function fix underscore incorrect underscore order calls the function serve underscore order by specifying the path to serve underscore order starting with super. Listing 7-8 calling a function using a relative path starting with super. The fix underscore incorrect underscore order function is in the back underscore of underscore house module. So we can use super to go to the parent module of back underscore of underscore house, which in this case is crate. The root from there we look for serve underscore order and find it. Success. We think the back underscore of underscore house module and the serve underscore order functions are likely to stay in the same relationship to each other and get moved together should we decide to reorganize the crates module tree. Therefore, we use super so we'll have fewer places to update code in the future if this code gets moved to a different module. Making structs and enums public. We can also make pub to designate structs and enums as public. but there are a few extra details. If we use pub before a struct definition, we make the struct public, but the struct's fields will still be private. We can make each field public or not on a case-by-case basis. Listing 7-9, we've defined a public back underscore of underscore house breakfast struct with the public toast field, but a private seasonal underscore fruit field. This module is case in a This model is a case in a restaurant where a customer can pick up a type of bread that comes with a meal, but the chef decides which fruit accompanies the meal based on what's in season and in stock. The available fruit changes quickly, so customers can't choose the fruit or even see which fruit they'll get. Listing 7-9, a struct with some public fields and some private fields. Because the toast field in the back underscore of underscore house breakfast struct is private, in eat underscore at underscore restaurant, we can also write and read to the toast field using dot notation. Notice that we can't use the seasonal underscore fruit field in the eat underscore at underscore restaurant because the seasonal underscore fruit is private. Try uncommenting the line modifying the seasonal underscore fruit field value to see what error you get. Also note that because back underscore of underscore house breakfast is a private field, the struct needs to provide a public association function that constructs an instance of breakfast. We've named it summer here. If breakfast didn't have such a function, we couldn't create an instance of breakfast in the eat underscore at underscore restaurant because we couldn't set the value of the private seasonal underscore fruit field in eat underscore at underscore restaurant. In contrast, if we make an enum public, all of its variants are then public. We only need the pub before the enum keyword as shown in listing 7-10. Listing 7-10, designating an enum as public makes all of its variants public. Because we made the appetizer enum public, we can use the soup and salad variants in eat underscore at underscore restaurant. Enums aren't very useful unless their variants are public. It would be annoying to have an annote all enum variants with public in every case, so the default for enum variant is to be public. Structs are often useful without their fields being public. So struct fields follow the general rule of everything being private by default unless annotated by pub. There's one more situation involving pub that we haven't covered, and that is our last module system feature, the use keyword. We'll cover use by itself first, and then we'll show you how to combine pub and use. Bringing paths into scopes with the use keyword. It might seem like the paths we've written to call functions so far are inconveniently long and repetitive. For example, in listing 7-7, whether we chose the absolute or relative path to the add underscore to underscore wait list function every time we wanted to call add underscore to underscore wait list, we had to specify front underscore of underscore house and hosting to. Fortunately, there is a way to simplify this process. We can bring a path into scope once and then call the item in its path as if they're local items with the use keyword. In listing 7-11, we bring the crate front underscore of underscore house hosting module into the scope of eat underscore at underscore restaurant function. So we only have to specify hosting add underscore to underscore waitlist to the call add underscore to underscore waitlist function in eat underscore at underscore restaurant. Listing 7-11, bring a module into scope with use. Adding use and path in a scope is similar to creating a symbolic link in the file system by adding use create front underscore of underscore house hosting in the create root. Hosting is now a valid name in the scope, just as though the hosting module had been defined in the create root. Paths brought into scope with the use also check privacy like any other paths. You can also bring an item into scope with the use and relative path. Listing 7-12 shows how to specify a relative path to get the same behavior in listing 7-11. Listing 7-12, bring a module into scope with use and a relative path. Creating idiomatic use paths. In listing 7-11, you might wonder why we specified use create front underscore of underscore house hosting and then called hosting add underscore to underscore waitlist in eat underscore at underscore restaurant rather than specifying the use path all the way out to the add underscore to underscore waitlist function to achieve the same result as in listing 7-13. Listing 7-13, bringing the add underscore to underscore waitlist function into scope with use is, which is Unidomatic. Listing 7-13, bringing a add underscore to waitlist function into scope with use, which is Idiomatic. Although both listing 7-11 and 7-13 accomplish the same task, listing 7-11 is the idiomatic way to bring a function into scope with use. Bringing a function's parent module into scope with use, so we have to specify the parent module when calling a function, makes it clear that the function isn't locally defined while still minimizing repetition of the full path. The code in listing 7-13 is unclear as to where add underscore to underscore waitlist is defined. On the other hand, when bringing in structs, enums, and other items with use, it's idiomatic to specify the full path. Listing 7-14 shows the idiomatic way to bring the standard library's hash map struct into the scope of a binary crate. Listing 7-14, bringing hash map into scope in an idiomatic way. There's no strong reason behind this idiom. It's just the convention that has emerged, and folks have gotten used to reading and writing Rust code this way. The exception to this idiom is if we're bringing two items with the same name into scope with use statements. Because Rust doesn't allow that, listing 7-15 shows how to bring two result types into scope that have the same name but a different parent module and how to refer to them. Listing 7-15, bringing two types with the same name into the same scope requires using their parent modules. As you can see, using the parent modules distinguishes the two result types. If instead we specified use std : fmt : result and use std : io : result, we'd have two result types in the same scope, and Rust wouldn't know which one we meant when we used result. Providing new names with the as key. There's another solution to the problem of bringing two types of the same name into the same scope with use. After the path, we can specify as and a new local name or alias for the type. Listing in 7-16 shows another way to write code in listing 7-15 by renaming one of the two result types as, using as. Listing 7-16, renaming a type when it's brought into scope with the as key. In the second use statement, we chose the new name io result for the std : io : result type, which won't conflict with the result from std : fmt that we've also brought into scope. Listing 7-15 and listing 7-16 are considered idiomatic, so the choice is up to you. Re-exporting names with pub use. When we bring a name into scope with the use key, the name available in the new scope is private. To enable the code that calls our code to refer to the name as if it had been defined in that code scope, we can combine pub and use. This technique is called re-exporting because we're bringing an item into scope but also making that item available for others to bring into their scope. Listing 7-17 shows the code in listing 7-11 with use in the root module changed to pub use. Listing 7-17, making a name variable for any code to use from a new scope with pub use. By using pub use, external code can now call the add_to_waitlist function using hosting : add_to_waitlist. If we hadn't specified pub use, the eat_at_restaurant function could be called hosting : add_to_waitlist in its scope, but external code wouldn't take advantage of this new path. Re-exporting is useful when the internal structure of your code is different from how programmers calling your code would think about the domain. For example, in this restaurant metaphor, the people running the restaurant think about front of house and back of house, but customers visiting the restaurant probably won't think about the parts of the restaurant in those terms. With pub use, we can write our code with one structure but expose a different structure. Doing so makes our library well organized for programmers working on the library and programmers calling the library. Using external packages. In Chapter 2, we programmed a guessing game that used an external package called rand to get a random number, to get random numbers. To use rand in our project, we added this line to cargo toml. Adding rand as a dependency in cargo toml tells cargo to download the rand package and any dependencies from crates.io and make rand available to our project. Then, to bring rand definitions into the scope of our package, we added the use line starting with the name of the package, rand, and the listing the items we wanted to bring into scope. Recall that the generating random number section in Chapter 2, we brought the RNG trait into scope and called the rand : thread underscore RNG function. Members of the Rust community have made packages available at crates.io, and pulling any of them into your packages follows these simple steps: listing them in your package cargo toml file and using use to bring items into scope. Note that the standard library std is also a crate that's external to our package. Because the standard library is shipped with Rust language, we don't need to change cargo.toml to include std, but we do need to refer to it with use to bring items from there into our package's scope. For example, with hashmap, we could use this line. This is an absolute path starting with std, the name of the standard library crate, using nested paths to clean up large use lists. If we were using multiple items defined in the same package or same module, listing each item on its own line can take up a lot of vertical space in our files. For example, these two use statements we had in our guessing game in listing 2-4, bringing items from std into scope. Instead, we can use nested paths to bring the same items into scope in one line. We do this by specifying the common part of the path, followed by 2 colons, and then curly brackets around the list of parts of the paths that differ, shown in listing 7-18. Listing 7-18 specifying a nested path to bring multiple items with the same prefix into scope. In bigger programs, bringing many items into scope from the same package or module using nested paths can reduce the number of separate use statements needed by a lot. We can use a nested path at any level in a path, which is useful when combining two use statements which share a subpath. For example, listing 7-19 shows 2 use statements, one that brings std : io into scope and the other one that brings std : io : write into scope. Listing 7-19, 2 use statements where one in a subpath is in a subpath of the other. The common part of these two paths is the std : io, and that's the complete first path. To merge these two paths into one use statement, we can use self in the nested path as shown in listing 7-20. Listing 7-20, combining the paths in listing 7-19 into one use statement. This line brings std : io and std : io : write into scope. The Glob operator. If we want to bring all public items defined in a path into scope, we can specify that path by following the star, the Glob operator. Use std : collections : star. This use statement brings all public items defined in std : collections into the current scope. Be careful when using Glob operator. Glob can make it harder to tell what names are in scope and where a name used in your program is defined. The Glob operator is often used when testing to bring everything under test into the tests module. We'll talk about that in How to Write Tests section chapter 11. Test section in chapter 11. The Glob operator is sometimes used as part of a prelude pattern. See the standard library documentation for more information on that pattern. separating modules into different files. So far, all the examples in this chapter define multiple modules in one file. The modules get large. When the modules get large, you might want to move their definitions into a separate file to make the code easier to navigate. For example, let's start from the code in listing 7-17 and move the front underscore of underscore house module to its own file, src/front underscore of underscore house.rs, by changing the create root file so that it contains code shown in listing 7-21. In this case, the create root file is src/lib.rs. But this procedure also works with binary crates whose crate root file is src/main.rs. Listing 7-21, declaring the front underscore of underscore house module whose body will be in source/front underscore of underscore house.rs. And the src/front underscore of underscore house.rs gets the definitions from the body of the front underscore of underscore house module, as shown in listing 7-22. Listing 7-22, defining inside front underscore of underscore house module in source/front underscore of underscore house.rs. Using a semicolon after mod front underscore of underscore house rather than using a block tells Rust to load the contents of the module from another file with the same name as the module. To continue with our example and extract from the hosting module to its own file as well, we change this src/front underscore of underscore house.rs to contain only the declaration of the hosting module. Then we create a src/house underscore of underscore house directory and a file src/front underscore of underscore house/housing.rs to contain the definitions made up in the hosting module. The module tree remains the same, and the function calls in eat underscore at underscore restaurant will work without any modification, even though the definitions live in different files. This technique lets you move modules to new files as they grow in size. Note that the pub use crate : front underscore of underscore house : hosting statement in src/lib.rs also hasn't changed, nor does use have any impact on what files are compiled as part of the crate. The mod keyword declares modules, and Rust looks in a file with the same name as the module for the code that goes into the module. Summary: Rust lets you split a package into multiple crates and a crate into modules so that you can refer to items defined in one module from another module. You can do this by specifying absolute or relative paths. These paths can be brought into scope by a use statement, so you can have a shorter path for multiple uses of the item in that scope. Module code is private by default, but you can define public by adding the pub keyword. In the next chapter, we'll look at some collection data structures in the standard library that you can use in your neatly organized code. Well, that concludes Chapter 7. Next we'll do Chapter 8.